Students of physics, hello. I have a serious question for you. How many stars do you see? How many stars do you see now? And now? And finally now? You can probably notice that the first image, it looked like one point of light. But as we progressively got closer to the image or images, you could finally resolve two sources of light. Resolve is the key word because we're talking about something called resolution. So we want to investigate how come we can get better resolution, distinction between two or more objects, as our distance to those objects becomes closer. Let's take a look. Resolution has a lot to do with diffraction. We just talked about diffraction last week. We just ended that topic, or kind of ended it, because now we're starting resolution, which ties into an application of diffraction, a natural application. As light passes through our eye, we get a diffraction pattern, and that hinders or helps our ability to resolve two or more images, meaning to make a distinction between them. So let's take a look at what this is here, in particular with our eye. Now, you may know that the eye is a circular or semicircular entryway for light. Now, it's a little complex to talk about the eye, but just in general, we know that light passes through the hole in the center of our eye that we call, do you know what we call it? That's called the pupil. Then it passes through the lens and it goes through some other structures, and eventually the light falls on the back of the eye called the retina. Now, since this is a little bit more complex, what we're going to do first is we're going to investigate light falling upon a camera lens. Little simpler to investigate, that's why we're taking a look at this. So light falls upon a camera lens, and as it falls upon the camera ends, the light diffracts. Now, if you remember in our topic of diffraction, we often talked about light passing through a small slit and diffracting. But you might remember light can also pass around a small obstruction and diffract. But usually those slits or obstructions were long, skinny, narrow ones. This time, they're going to be circular obstructions, like the opening to the lens. And it's going to produce not a long, skinny diffraction pattern, but a circular diffraction pattern. The same kind of thing happens within our eye. So you're looking at a circular diffraction pattern here. You're seeing the actual light in the center. Then you're seeing interference patterns between dark and bright fringes. And that fringe effect is a diffraction pattern. Now, if you got a larger camera lens, or a larger eye, but we're kind of stuck with the eye we have, but a larger camera lens, then we would be able to cut down on our diffraction, meaning the image would not have the appearance that we're seeing right here above, but would be a much smoother looking appearance. So why wouldn't we just do that all the time? Well, there's a trade-off. See, when you get a much larger lens, you also lose the depth of vision. Depth of vision is your ability to keep the foreground and the background in focus at the same time. So if you have a good depth of vision, that means the foreground, whatever you're seeing up close, and whatever you're seeing far in the back, are in focus together. And there's settings on digital cameras especially that will allow you to do that. But the good depth of vision, the low diffraction means that we have a poor depth of vision at the same time, which means what we see in the foreground and background will be out of focus with each other. So what I'd like you to do right now is take out a very small piece of paper, half sheet, index card, something like that, and just write down on it your name and the definition of depth of vision that I just gave you. Turn it in the next day. Let's keep going. Exactly what I just described for the lens also goes for your eye. So as we get less diffraction, if let's say the lens could accommodate and open wider, we lose our depth of vision. Now what we're taking a look at here is a diffraction pattern formed by something like a lens, or the diffraction pattern formed in the back of the retina. And this is a 3D representation. So the spike right here is the bulk of the light that gets through, but this ring around the outside is an interference pattern formed by diffraction. Here it is in an actual picture. So you may have seen before, when you look at a bright source of light, there's a haziness around the outside of the light. And this haziness around the outside is a result of diffraction taking place. Astronomers see this all the time. So here's a picture looking through a telescope at stars in the heavens, and you can see how there's this bright spot of light with the haze effect around it. That's a result of diffraction happening through the telescope and also being broadcast onto the back of the eye, the retina, where the image is received by the brain. Now, here's 4 different pictures of a plant. And you can see that it starts off with the foreground and this image here of this leaf, very crisp and very clear. But what happens is the aperture size is continually reduced all the way down to the last one. So if we compare the first and the last, the aperture being reduced, and that's accomplished by raising the f-stop setting on a camera, causes the diffraction to increase. So the diffraction here, the diffraction pattern, though you're not able to perceive it perfectly, you can see the effect that it has on the image is more of a blurred sort of image, a hazier looking image. Now remember, the trade-off is that when we have more diffraction, we get a better depth of vision. That means the foreground and the background would be more in focus with each other. I know that's arguable here because it looks like this picture, you can clearly see the foreground and the background, but remember, in this particular picture, there's hardly any depth difference between the foreground and the background. One more time, and this summarizes it here. We have a lens with a small opening, and so we get more diffraction. As opposed to a large opening down here, less diffraction. When we have the small opening and the increased diffraction, we have a greater depth of vision, foreground and background in focus with each other. When we have less diffraction because of the large opening, we have a smaller or less depth of vision, which would mean that the foreground and the background would not be in focus with each other. Now what we're going to do is we're going to take a look at how we can resolve images, and in particular, what affects our ability for our eye to distinguish or resolve 2 images. Remember, resolving images is being able to tell the difference, distinct difference, and there's certain criteria you have to meet here, but to tell the distinct difference between 2 objects that are either emitting light or reflecting light.
We have clearance, Clarence. Roger, Roger. What's our vector, Victor?
Okay, so here's someone piloting a hang glider. Took me a second to remember what that was called. And you can imagine if you were in this hang glider, the higher up you got off the ground, the harder it would be to discern and distinguish or resolve details of what's on the ground. So let's say we placed a couple silver dollars on the ground, maybe a foot, 2 feet, 3 feet, no more than that apart. If you're standing directly over them, you can see 2 silver dollars on the ground, a few feet apart. The higher you get, the harder it is to distinguish what they are, and pretty soon they kind of morph into one blob, and it's hard to actually see the difference between either of those 2 silver dollars. So here's that exact situation. The person who's observing the 2 silver dollars and spot object 1 and spot object 2 is up here, and we'll pretend like they're just looking at it through one eye. Now realistically, they're probably looking at it through 2 eyes. The distance between their eyes is close enough that it essentially goes to one spot in particular. And can they discern the 2 objects? Can they tell the difference between them? Well, let's say if they were starting really low down here. You see the angle theta that's measured up here? We call that the angle that subtends their view. That's an angle formed from where they're looking to object 1 and where they're looking to object 2. And that angle right there is exactly the size that you're seeing.
I sense much fear in you.
Now don't be afraid. If this person was lower down, say where my red dot is right here, then the angle will be bigger. Imagine drawing an angle from right here, where my red dot is, to where both of those are. The angle would be bigger. Now, as they get higher up, that angle becomes smaller. There's a point where they're high enough and that angle is small enough that they can no longer resolve the difference between those 2 objects. Those images are no longer discernible as 2 separate objects. They kind of look like one overlapping object. So we'll say that in general, that as the angle decreases, because their height increases, their ability to resolve the 2 objects is not as good. Take a moment and pause the video and write that detail down. Now here's a picture of a car approaching from C to B to A. If you just looked at this, you would say that A, it's the closest, and that's no surprise. But we know that the photographs are taken at different distances, and as the car gets closer, we can discern the difference or resolve the two headlights better than we could before. See, in this first one, you can kind of tell it's two headlights. You have the gist that it's not a motorcycle with a single headlight, but you can't really see the distinction between them. This area between here is not discernible. It becomes much easier here, and it's very easy here. So I would say probably right around this spot here in picture B, the two objects are just becoming resolved. Take a moment and pause the video and write down the definition here of resolving power. Continue on when you're done. Now, how do we increase resolving power? Well, there's different fancy ways to do that. Obviously, one idea is if the image is closer or appears closer to us, then the image or the two objects are more resolved. We can tell the difference between them. If you think back to the slide that had the hang glider, when the hang glider was close enough to the two objects on the ground, the angle, that word subtended is here again. So the angle subtended was big enough. When that angle is big enough, then you can discern between the two objects. You can resolve them. Remind me to show a few drawing variations of this in class the next day. Now, if that angle is too small, meaning that they're too far away from the objects or they appear to be too far away, then that angle being too small means that they can no longer resolve the difference between the two objects. Now, being able to increase our ability to resolve or resolving power becomes quite important, especially when we start to turn our gaze toward the skies, toward the heavens, and we start to look at systems that are made up of more than one point of light, such as a binary star system. To the naked eye, we would probably look up there and see one point of light, and we'd think that's a star. Throw a telescope on there, and all of a sudden our ability to resolve is better than it was before. And we might be able to determine, oh my goodness, that's actually a binary star system. There's two stars. Or we might be shocked and find out we're not looking at a star. We're looking at a galaxy made up of billions of stars. So when we turn our eyes to the heavens, we're actually kind of being misled because some of those points of light are entire galaxies all on their own. Now, what we're going to get into next is figure out exact criteria that we can lay out that will help us to know what is the situation that we are in when we can exactly start to discern or resolve between two sources of lights. That is it for now. Take care.